So Nikolai Lipscomb is a research staff member at the Institute for Defense Analyses, and he works within the Science, Systems, and Sustainment Division at IDA. Prior to his work at IDA, Nikolai graduated from the Department of Statistics and Operations Research at the University of North Carolina in Chapel Hill. His research experience includes stochastic modeling and numerical optimization. Without further ado, go ahead and begin.
Hi, everyone. I apologize. I have been the sickest, or I was the sickest I've ever been on Monday and Tuesday. And you might end up with a slightly Ben Steinish presentation today. Deep sighs between very dry periods of text. So apologies. And, my responses to questions, we'll see what quality you get. I know stuff pretty well, though, so. So this course is, geared towards, if you read the abstract, if you have some experience with machine learning, a lot of this might be stuff you've seen before, but this is mainly focused at people, have some good mathematics background, want to understand, machine learning workflow a little better, and also focus on the interpretable aspects. There's been a big, I wouldn't say recent, this has been ongoing for some time now, but there's been some pushback against uninterpretable models, when interpretable models can often do better. I think the biggest example I can think of that really got news attention was COMPAS, COMPAS. Back in the day, that was for criminal recidivism. That's actually taught at law schools now. Yeah, that's how big it was. It's not just a statistics, mathematics thing. So anyway, machine learning tasks, things we might do. I have examples here where, a simple task might be trying to estimate fuel requirements if I have all this data on a search and rescue mission. Things like vehicle specification, route details, terrain, weather information, so forth. Another type of task, one that we're probably quite familiar with, is automatically quarantining malicious emails. Often with emails, you're dealing with free text data, which can get, very complex, as you can imagine. That usually falls under natural language processing. But there are ways to process the text to deal with things like keyword frequencies, where, if you see the word warranty popping up too much, or car's extended warranty popping up too much, it's probably spam email. There are a lot of sort of decision problems that show up under machine learning. There's the good old, automated vehicle type problem where you have to, adjust trajectory and acceleration of an automated vehicle. And the sort of data you might have to deal with that is, could be multimodal. So you might have camera, computer vision type data, LiDAR maps, other different sensor readings, in addition to, obviously the current trajectory and velocity. And then something that I, do with a bit more myself is where I'm looking at logistics networks. It would be helpful to have things like historical demand, and then, of course, expected cost rewards associated with different routing actions. So there are a lot of complications in machine learning type tasks. A lot of it has, often comes from, the dimensionality of the data. And I'll talk a little bit about dimensionality in a moment. The first issue you can have is obviously having insufficient data, right? You might be trying to estimate something very complicated, like that fuel requirement, but maybe you only have half the picture, in which case, you're going to be limited with respect to your data. Free text and images, those are cases where the dimensionality is high. If you think about it, a 24 by 24 image in black and white is already 24 squared variables. And those will basically take on values based on pixel intensity. So as you can imagine, high resolution images get very large, add in red, green, blue coloration, and you're already dealing with very massive state space. So a lot of machine learning is trying to, trim the model down and look at what are the salient parts of the image, or what are the salient parts of the text. I will say up front that machine learning techniques that do best with images and natural language are usually not the most interpretable. Those usually go into the land of neural networks. But there are a lot of classical machine learning tasks that can be performed better with interpretable approaches. And there is this tendency I've noticed, online and talking to practitioners, there is a strong tendency to lean towards neural networks for whatever reason nowadays, which I think is a little bit dangerous if they're too convoluted. So I mentioned there's a low dimensionality. Goodness gracious, my throat. There's the low dimensionality issue, the high dimensionality issue. You can imagine all sorts of other problems, such as if you have multimodal data, you could have contradictions, spurious signals, between different sensors. I'm sure you can imagine many other different complications that would come up on your own. I think we'll be focusing more on the high dimensional aspect of things, where we have a lot of data. Some of it, may not be easy to determine what's useful and what's not useful. A simple way to prune a model is be like, hey, I have SAT scores and I forget the other alternative to the SAT. ECT, is it? ACT, ACT, yes, thank you. And it's like, if you have both you're trying to predict someone's college GPA using their ACT and their SAT score, well, they might be, more or less highly correlated, right? In which case, using them both might be kind of redundant. So that's like, perhaps a simple example of where I need to reduce the feature space. But a lot of the case, it's not such an easy determination to make. So as far as, I'm going to bring things back to interpretability as we go on throughout this talk. And this is, an image I made up because, what is interpretable? This is very subjective. What is complex? That's also subjective. But the general idea is that when you're dealing with, machine learning models, there's usually a trade-off between interpretability and complexity. And for the most part, like, complexity usually allows you to do more complex things. So complexity often increases capability. You could do, for example, linear regression, which is, something of the form like y equals mx plus b, for example. I could process text data to accept, to plug into a linear type model, but it might not perform very well compared to a state-of-the-art, transformer network, for example. My personal favorites are decision trees. There's actually, I'll be pointing you towards some cutting-edge research in the field of decision trees. A lot of the issue with decision trees is that it's a complex optimization problem. So a lot of the work is on better solving the optimization problem. We'll talk a little bit about computational complexity in this talk as this ties into interpretability in the sense that some simpler algorithms, you can always kind of more or less know that you're going to get the same result when you solve for an optimization problem. You'll get the same thing each time, whereas there are other optimization algorithms where it's almost like a random search, and you just try to find the best solution you can get. And that can lead to, a question about, well, person A used the same data and got this model, person B used the same data and got this model. Why are their answers slightly different? That might be an aspect of the optimization part of the problem. I like to introduce machine learning concepts using linear models. So linear regression, logistic regression, which some of you may have heard before. If you have not, that's fine, because I'll be giving you a quick crash course in that while I introduce the machine learning aspects. But my general rule of thumb is, you can see it in this little black hexagon, or hexagon. I should have used pentagons. Makes sense for DoD, right? Oh well. what's the minimum capability you need to accomplish your task, right? Draw some sort of line there, and then try to go as high up on the interpretability as you can get. Again, this is very subjective. Things like clustering and matrix factorization, those are generally associated with unsupervised methods, which I'll talk about momentarily. Those are tackling very different problems from linear regression. So it's, even though they both have high interpretability and matrix factorization is, mathematically more complex, doesn't mean that it's giving you the same, necessarily giving you the same thing. So interpretable models, why do we like to use them? Well, they make it easy to communicate findings. That's one quick issue. And it also allows for quick diagnoses when you do run into issues. A good rule of thumb is to test multiple models, right? And then see, which model, is performing the best, but also like, are they more or less in line with each other? If you have multiple models and you have, one standing out, that's, giving like a very opposite answer to what you have in the other ones, that could be a sign that maybe you're missing something in the data, or maybe that model just happens to be wrong because it was, I don't know, too dependent on an outlier or something like that. But, these are some, examples I made up. So first question was, why is the search and rescue cost estimated to be almost double the last one, despite the length, area, and staffing of the mission being identical? Now, in my imagination, this was a very simple model that you literally stare at the equation for. And staring at this equation, I said, well, unlike the last mission, this search and rescue operation takes place over a mountainous region, which leads to higher fuel costs. So in our estimation model, this more than halves the mile per gallon efficiency of rescue vehicles. And based on historical mountain SAR operations, where fuel is the primary driver of cost, we believe this estimate is accurate. And you could literally point to the equation. This is how we got this value. And I think that would be a very acceptable answer. Let's look at the second one. This new logistics routing model underperformed relative to the previous year's approach. I think we should roll back to the older modeling approach. Well, my response would be, well, okay, our model was trained on several years of historical data. However, this past year was a significant outlier compared to the historical pattern. The older model also would have underperformed in these conditions, even worse than our new method. Further, there is strong evidence that we will return to the usual up-tempo. That is, I expect our logistics routing model will dominate the older model. So this is something where I would say, we still have a good handle on the model. We can look at the previous model, and the previous model would have performed worse than the current model. As far as, these logistics problems, usually routing problems are a very, very massive search space. So it's not very likely that we have the best model, but it's likely, we could have like a pretty good model. And the last example is, well, I'm sure we can draw an analogy to real life, but suppose my Nikolai's self-driving car suddenly drove into a pedestrian even though I was sitting at a red light. What happened? You can't trust a person with lie in their name, just as a warning. So the pedestrian was holding up a poster with a green light traffic signal printed on it. Unfortunately, since the system only uses computer vision for object detection and recognition, it was tricked by the poster. Pedestrians carrying lifelike images of traffic signals had not been explored yet in training. Also, if we incorporate other different sensor types, such as LiDAR, maybe radar, I don't know a whole lot about sensors, we could have perhaps recognized the computer vision signal as false. So in that case, I think my answer is satisfactory, but you have to keep in mind this, the set of all images is very, very, very large. As I mentioned before, if you're only at 24 by 24 in terms of pixels, and that's just in black and white, you're already at 24 squared. So imagine what, these high resolution images look like in terms of the actual variable space. But my answer to this was basically like, we didn't train it on stuff we hadn't encountered. And I guess now we have to, train it for fake, to handle fake green light signals. I don't know if there will be a good way to rely, at a certain point, humans will be able to trick the machine, right? I think there was a case with, some of you all might remember this, BAE, I think it was BAE. This was on the news a few years back. They had created I think it was like an automatic targeting module using computer vision only. And I think it was like a couple of Marines that tricked it used cardboard boxes. They were like inside cardboard. There were a lot of like Metal Gear Solid jokes after that. But they hadn't trained it on cardboard boxes, so it got past. And you can imagine all sorts of weird like niche cases you could implement to trick the machine. Okay, so machine learning is massive. We're only going to have enough time for a small bit of it. There's this whole field called unsupervised learning. I would say, I know this course is called Interpretable Machine Learning. I would say almost the entire scope that I can think of for unsupervised learning is making data more interpretable. But it's not necessarily goal focused in the sense that it's not like trying to estimate like fuel. It's not trying to, classify something. It's not trying to pick an optimal decision. What it might be doing is trying to, reduce the dimension of the data into maybe a new coordinate system where the coordinate system is more easily understood or something like that. So towards the end, I'll point out some references, that incorporate the unsupervised stuff. Supervised, on the other hand, so these are generally focused at learning a function. This function could be, hey, I want to learn a function that estimates, of our SAR. I want to create a function that estimates the probability of something being, a malicious email or not. I want to learn a function that tells me the long-term expected reward for taking a certain logistics routing action or a certain, vehicle, change of direction and acceleration action. There's online and offline learning. So the idea with online, so for each machine learning algorithm, you're going to have an optimization problem. And the idea is that in the online context, the optimization problem will intrinsically look to incorporate new data as it comes in. And I mean, that seems like something you should just naturally do, right? If you have new data, you should incorporate it. And that is true. Offline learning just looks at all the data that you have up until a certain point, and then it basically builds your model based off of, this data. And then you have your model, and it's up to you if you want to create a new model once new data comes in, right? But the incorporation of new data is not built into the optimization problem itself. So I think the canonical example of online learning is reinforcement learning, which, some of you may have heard of. And that's because, it's basically dependent on new data coming in. You see new data, you make a decision, and you reward or penalize yourself based on the outcome. Learning the reward over time requires a constant stream of data, whereas in the offline case, which we'll be focusing on specifically regression and classification, you just take all your data at once and then build your model off of that, and then make your predictions or classifications. And then if you need to tune your model again, that's up to you. It's not part of the optimization. Okay, so I'm going to quickly dive into a couple of examples that will introduce us to some of the concepts in this course. So for regression, I'm gonna my canonical running example for regression will be I want to estimate the monthly demand for a particular aircraft part, and I'll just say next month's demand. I don't want to I would like to, but it would be harder to forecast further into the future. But even predicting next month's demand is pretty useful. And what sort of data might I have? I could have like this month's demands, right, or the previous months if we're predicting the current. You could have things like flight hours per month. You could have, or planned flight hours per month. You could have things like average temperature per month. you could have whatever you want. You could have the number of dolphins in in Antarctica or off the coast of Antarctica at any particular time. You can have a lot of spurious variables, right? And the idea is that some of these you might need to trim down because we've incorporated too much, and we're more or less modeling random noise in the data. The idea is that if you can get a better and better fit by just adding more data, even if that data is nonsense. Right? Eventually the dimensionality of your space will be large enough that you can fit whatever you want to it. So we want to avoid that. And in regression, all we would do is we'd try to create some sort of plane in some sort of space, or a line if we're looking at one-dimensional predictor space, and just predicting y. So predictor spaces is just the set of predictor variables, one-dimensional, in this image here. And we'll look at another type of linear model. Now, I know the blue line's not linear, but I'll explain why it's linear later. Logistic regression is another example. And this example, we could look at, some sort of simple binary classification. You can obviously jump to more than binary, but in this example, we'll look at penetration versus non-penetration, for a specific platform. And we can have data such as armor material, thickness, temperature, humidity, munitions type, and so forth. In this case, we'd be modeling probability of penetration, and that probability could be used to make an assignment. If the probability is large, then we would assign it a penetration class, and then non-penetration if the probability is low. Now, the machine learning fundamentals we'll want to be familiar with, especially if we want to do some further reading on our own, is principles of optimization. Now, optimization, you'll have learned some of it even in Calculus 1, like setting the derivative equal to 0 type optimization. And it can get a lot more complex when you start bringing in constraints and non-differentiable functions. But the idea is you'll have some sort of measure of badness, I'll call it, which we call a loss function. You just want to make your badness small, right? Make it as small as possible. And you might have some constraints on the optimization. There'll be an example of what sort of constraints later, but I might simply some sort of restriction on what I'm allowing my model to do. And the idea is, some of these loss functions may be hard to minimize. Other functions may be easy to minimize. And the idea is that convexity is an important concept in optimization because convexity, usually means that if we can find a solution, well, I should say strict convexity. But if we can find a solution, we shouldn't be able to find like another one that's identical to it in a different point in the feature space. If I said regular convexity, you can, but the idea is that, you might have multiple solutions that have the same objective function or value for the loss function. So I think in the literature, objective functions are used for f as opposed to loss function. And constraints are usually just called like constraints or regularizations, just so you know. Statistical fundamentals are important. There's a bias variance trade-off. I'll talk about that in more detail. The curse later. The curse of dimensionality, that is, big data is hard. And then model selection / hyperparameter tuning. So a big part of machine learning is that you'll be comparing a lot of models. One simple case is, I want to consider a bunch of different subsets of predictors to use. Because, I could use all, 10 trillion of them, or I could use a bunch of different subsets of the variables and perhaps get a better model because I threw out, a bunch of extraneous variables I didn't need. And testing and validation. Now, keep in mind, this is not the DODM validation definition. This will be more focused on statistical validation. Okay. So regression, linear regression is, is a very good foothold for explaining a lot of these concepts. So those of you not familiar, this basically some sort of plane equation or depending, you might call it a hyperplane or whatever. But the idea is that, I have the thing I'm trying to predict, which is, demands for the next month. And the things I have are, okay, I have, that month's planned flight hours. I have last month's demands. Maybe that's a good indicator of what I'll have the following month. Then I might have things like average temperature. I feel like temperature probably impacts, right? Breakdown of parts, right? Seems reasonable. Planned sorties. I know you're already including planned flight hours, but you have to consider each sortie includes, a takeoff and a landing, which can produce a lot more stress than, just flying. So, I would say two 2-hour sorties might cause more stress than 1 4-hour sortie. And this is very simple to explain, to someone who wants to know, hey, X1 increased by 3, we increased our planned flight hours by 3. How is that going to affect our demands per month? And we're going to say, oh, well, since the coefficient of X1 is 5, right? 5 times 3 is 15, so we'll expect 15 more demands. I'm not sure. I'm making these up, of course, because hopefully nothing breaks that quickly. Now, a question we should have is, does a linear relationship seem reasonable? So this is, again, a notional example. But the idea is, those of you familiar with linear regression, you might try to find the line of best fit. And we'll build up to formulating that problem. But as I mentioned, all machine learning problems are the result of some sort of optimization. As I mentioned, if you have a regression equation, it's very, very interpretable because you know exactly how x's are interacting with your prediction output via the betas. So if I wanted to use number of scheduled preventative maintenance actions to try to predict demands per month, then my profile looked like that. Perhaps this red line of best fit would be a very good predictive model. It looks pretty good in my opinion. But how would we format exactly? This is where we have to set up some sort of optimization problem. And as I said, for optimization, you need some measure of badness of your model. And, a measure of badness could be something like, how far off am I? I could look at the absolute value of the deviations. Another approach that is the standard approach for least squares regression is look at the squared differences from the model. Which one is better? I think you just have to consider, how important are outliers to you. But, set this up, you would just look at your, just sum up all your squared errors, right? This is your actual value versus your predicted value. Now, if you had a perfect fit, that would be 0, right? All your data would lie on the line, right? And you'd have 0 errors, right? That's not going to be the case. But one reason why the squared loss, squared error loss is so important, or squared residual loss is so important, or is so popular, I should say, and important, is that it's, it ends up just being like a parabola type shape, right? In which case you can just, and it is differentiable. I do like writing it in vector form. This basically says the same thing as what I had in the previous slide. And basically, you don't have any constraints to worry about. Constraints always add complications to your optimization. But you can literally solve for it and using calculus or linear algebra and vector calculus and get these matrix equations. One thing to note is that if we have a lot of data, there's a risk of X transpose X being, close to singular. So singular is, if you have something as singular, you can't take the matrix inverse of it. If you have something that's close to singular and try to take its inverse, what you have is numerical blow up, where the values will just be massive, supermassive. So that's something to worry about because that actually is going to give you the variance of your predictive model. And I'll show you why variance is too much variance is bad. One quick thing to note is that, these are just, some examples. So you have, I mentioned like convexity is a nice property to have. If you have regular convex, basically you can say, okay, I have a minimizer and it's like but it might be across like many different values. You can have convex functions that don't have a minimum, like if they, still have like, positive gradients or increasing gradients, but asymptotically trail off to some lower value or something like that. But usually, once you have existence, uniqueness is provided by having a strictly convex function. And I think, when you talk about quadratic functions, since we know there's an inflection point, I forget the exact definition, but I think it might be strong convexity. But the main issue is a lot of machine learning, we try to avoid these things called non-convex functions. And the idea is when we minimize functions, like one of the most popular approaches is gradient descent for the unconstrained case, and then interior point methods for constrained cases. And one simple way to look at it is if I just took a random point and then dropped water on it, and we'll assume frictionless surfaces, et cetera, the drop of water should eventually like fall to the bottom of your curve, right? For the non-convex case, though, it's really like, if you drop, I guess it's not showing. Well, you can see if depending on where you drop your water on the non-convex function, it could end up in this minimum versus the other minimum. There might be other like local minima in other directions, but that's an issue, is that it's kind of up to luck in a sense, whether you get a true global minimum or not. One thing I will say, this is a common problem in deep learning architectures, and they still do well. Even if you can't get a global minimum, you still get like a pretty good, a local, you can see that, if we got this local minimum, it's not much worse than the global minimum on the left. Okay. So regression model, so we solve this, minimizing the sum of squared errors, and we end up with this this model. And the idea is that we need to do some sort of statistical validation. So for this, usually what we do is we'll build test and validation sets using our data. But we'll also need a scoring method, that tells us the goodness of our model. And these scoring methods generally look at your errors. I use the term residuals because that's popular in the literature, and a lot of the time you're saying the same thing in machine learning. Errors, residuals are the same. Loss function, objective function are the same. Residuals, can be zero, positive, or negative. Zero means perfect prediction, right? But you can underpredict and overpredict. And generally what you like to see from residuals are what we call unbiasedness. And that means that on average, you're missing by zero, right? You might be overall missing, right? You might not ever hit on target, but on average, you're getting zero. High variance is like the shotgun spread, where you're maybe you're unbiased, but when you miss by a lot, and you'd rather your misses be on the low side. If you can find something that's both unbiased and low variance, that is great. But generally, you're going to have a lot of the time you're going to see some sort of trade-off between the two, and that will lead to the bias variance trade-off. So speaking of the validation test set approach, basically what we do is you have your full data, and then you would basically split it up. There are many different ways to do it. Like assuming you're not dealing with like specially formatted data, or but you could just use kind of your standard sampling methodologies. For example, if I think all the observations are IID, identically independent, identically distributed, I could just do like simple random sampling would be one approach. And the idea is that I only train my model in the training set, because as you imagine, whatever you train, is going to be biased to do well on the training set, right? It's like, you know, it's like grading your own homework, right? So validation set, or you know, some people call it a holdout set, some people call it a test set. So those are, again, three names for the same thing. That is what we you know, evaluate our model with respect to, and then we look at the scores that we get with respect to the validation set. The idea is that we would usually do this multiple times. So you would have multiple validation sets, multiple training sets, and then you could kind of look at the aggregate scores across all those sets. One popular approach is called K-folds cross-validation, and I'll introduce that a little bit later. But each fold is basically, you know, you split your data into roughly equal pieces, and basically everything except one of those pieces acts as training. So you have, like, if you had 5 folds, you'll have, like, you know, 4 training folds, 1 validation fold, and then you just swap out which one is the validation fold. I'll illustrate that a little bit later with a picture. As I mentioned, a big part of machine learning is comparing multiple models. So this is the super simple case. And again, this, you know, relating this to interpretability, you know, obviously, like if you have like so much data, you know, obviously you want to get rid of what's extraneous, right? Again, this is a simple case. You know, no one's going to be intimidated by 2 predictors. You've got, you know, maybe you only have a 2 predictor model. Well, you still got a few like simpler models you could consider. You could have, you know, I don't believe any of the predictors are useful. I'm just going to use the mean value. You have the I only think predictor 1 is good. I only think predictor 2 is good. And then, of course, you have the full model. So you might try multiple models and test their scores on validation sets, right? And then see which performs best, and then pick that as basically your winner. One nice method that I think has a generally well accepted interpretation is the R-squared statistic. Again, you do this on your test set results, and that essentially uses the error. It's essentially a ratio of like your model error to the null model error. R-squared, I think if you Wikipedia it, it will, quote, give you, R-squared gives us the percentage of the variation in the test data explained by the model. I read that as robotically as most people will read it if they look up R-squared. And remember, it's going to be unbiased if you're doing it towards your, if you're calculating it from your test data, right? R-squared actually, as you add more and more variables to the mix, R-squared will always go up with respect to your training data. But with respect to your test data, well, it'll usually go up to a certain point, and then adding too much data will start to hurt your R-squared. So R-squared, so it's going to be between 0 and 1. I gave you kind of that, nice percentage of the variation explained by the model definition. If you're comparing multiple models, simply, pick the model with the highest R-squared score as your winner. And just keep in mind, always make sure that you're not, calculating R-squared. I mean, you can calculate R-squared with respect to your training set, but don't use your training set as your measure of success, because, the bigger model will always win in the training set. If you think about it, right, if we jump back to this, right, and we compare univariate model 2 to the full model, right? I can we're trying to find the best betas, right? I can clearly get univariate model by just saying, all right, let's find the best, but force beta 1 equals 0, right? So it's basically saying, am I going to do better by, by fully unconstrained optimization, or can I do better by doing fully constrained except this one restriction? Clearly, if I'm fully unconstrained, right, I will do best. Okay, so I'm going to talk about bias variance trade-off. Again, I use kind of like this rifle example. Basically, like bias is like your scope is misaligned, right? You're missing on average not a non-zero amount. Generally, if you have too many features, or if you have too few features, rather, you'll tend to have something with like high bias, but not a whole lot of variation. And if your model gets like very, very complicated, for example, by adding features, you'll generally get, something with, maybe not a whole lot of bias, but it kind of just goes all over the place with respect to its prediction values. This is an example where maybe you use something called basis linear regression, where you just use a polynomial basis as your polynomial basis expansion for your data. And that would be if you had one variable that was like x, you would also include x squared, x cubed, x to the fourth, and so forth. In this example, you've got kind of, the pink line, which is an example where, I just used x, a straight line with respect to x, the horizontal axis. The blue line is I used, a high degree polynomial to fit to the data by adding a lot of extra data. And the idea is, which do you like more? I mean, I don't really like either of them. Maybe something that was more like, like a 1 over x type shape or something like that, but repositioned in the right place. But this does demonstrate the idea of, okay, here, like the pink line, we're kind of, we're probably missing on average, but as you can see, like the predicted values aren't going to be like, scattered out all over the place. Whereas for the blue line, yeah, we use more data to get, a tighter fit to the training data, but it's also going to, for values in kind of this range on the x-axis, it might predict, unusually large y values, right? And then similarly, in this x-axis range, it might predict unusually low y values. So that's something that will arise from having too much. So this image basically discusses what I was talking about before with, for R squared and, a lot of scoring methods in general. R squared, will always get better, as your model complexity increases, as you add more and more variables. But the validation is going to be like, all right, there's a certain point where we're adding, junk to the mix, right? And we need to stop adding variables. At that point, we're modeling random noise. That random noise is present in the training data, right? So we're going to do great in the training data, but we're not going to do great. We shouldn't be extrapolating that to the general case. So I've given a long spiel about these principles. As I mentioned, there are a lot of computational bottlenecks involved in machine learning problems. I gave the 2 predictor example, but what if we had 10 predictors instead? So, obviously you have the null model, you have a bunch of univariate model, you have a bunch of bivariate models, trivariate models, so forth, and you have the full model. You actually end up with over 1,000 potential models just from having 10 predictors. That might not sound terrible, right? But 10 predictors is kind of small, right? Usually when I'm dealing with data, I'm dealing with, hundreds. And if I'm dealing with images, I'm dealing with millions. So one approach is to use exhaustive selection, but if you use exhaustive selection with 100 predictors, you're already looking at like 1.27 times 10 to the 30th models. I don't think your computer will run that, or maybe it will. I don't know. So there are a lot of like heuristic or kind of greedy algorithm type approaches to help the predictor space be more manageable. Stepwise selection might be one of the most well known. There's also like a statistics-based approach to stepwise selection. What I'm doing is more what I'd call the machine learning approach. It doesn't make any distributional assumptions. But the idea for stepwise selection is, I start with no predictors and then I say, if I add one predictor, how much better am I going to do? All right, now I've added that one. What's the second best predictor I could add? And then I add that second best predictor. Eventually, I'm going to reach a point where adding a new predictor might be making things worse on the test set. It'll always make things better on the training set. Or I might have some sort of cutoff like, once the improvements are beneath epsilon improvement, then I stop adding stuff. You'll see that this is already a huge computational improvement on exhaustive selection, but again, no guarantees on it being the optimal model. We'll talk a little bit about regularization. I'm not going to talk about matrix factorization approaches, but you're free to look up like principal component analysis is very popular. Non-negative matrix factorization is another very popular one. So as you can see, like in the number of predictors you have this factorial growth. Factorial growth actually grows faster than the exponential function, but usually in you have to look out a little bit far to see that. Quadratic growth or polynomial, a low degree polynomial type of growth is what we get from the forward selection approach. So already you can see, if your number of predictors are low, it doesn't really matter what you use, right? But if we look at log scale, number of fits to data, that's how many times you have to train, based on each model. You can see that the factorial growth, which looks linear and exponential, is vastly outgoing the forward selection. So that, again, like comparing multiple models, so that's one approach you can take. I'll talk about regularization. So as I mentioned before, when you're looking at lots and lots of predictors, right? It can be hard to kind of go through your data and look at it manually, although, one thing that you have to watch out for in linear models, or just, any model in particular, is when you have highly correlated predictors. And the idea between high correlations is they might just be redundant, right? So we might have, GRE and LSAT, for example, two graduate tests. Maybe they're both testing the same thing, for example. Now, if you could look at a correlation matrix, and again, like correlations, these are looking specifically at linear correlations. So, these correlations look like this. Like, for example, if you had perfect positive linear correlation, you'd have 1, right? Perfect negative correlation, you'd have -1. But you can also have in between values. For example, this big blob in the top center, you could fit multiple lines through it, and I wouldn't say one is better than the other. But something like second on the left on the top, like 0.8, has a loose, maybe not too loose, like a pretty obvious positive trend. You have issues with the stuff on the bottom row, where you have like perhaps these clear patterns like the W. Sure, I can fit like some sort of polynomial through it maybe, but the idea is that it's not detected because this only examines linear correlations. But you could, if you have your data, you could look at like the correlation matrix and just be like, oh, hey, I have all this data. Obviously, like, the diagonal is all ones because everything is perfectly correlated with itself, right? That might be like, oh, well, okay. Variable 4 and variable 0, right? Row 4, column 0, and it's symmetric, right? 4 is correlated with 0, the same as 0 is correlated to 4. Okay, those have a pretty high correlation. Maybe I should take a look at these and be like, are these saying more or less the same thing? Now this is a 9-variable case, right? We have, and as I said, we're often dealing with hundreds, thousands, perhaps more variables. So looking at the correlation matrix might not be super helpful because it'll just be too dense, right? So instead of going through things, well, maybe I can take this regularization type approach. So for the linear models, one thing to note is that if you have highly correlated variables, that will likely lead to this matrix being close to singular or ill-conditioned, which again can cause your coefficient estimates to blow up. So like one simple way is to, simply put some bound on the betas and just be like, I won't allow betas to be too big. We're still keeping the general interpretability of what the beta values mean. All we're saying is that, there's some sort of restriction on how big they can be. There are two ways to do this that are popular. The most popular way to do it is kind of adding what we call a penalty function. It looks kind of like a Lagrange multiplier type thing. Or you can add a constraint. And this is where I start introducing this concept of hyperparameters, which I've only mentioned in passing. So there have been model parameters like the betas that we tried to determine from a model. But now, but the model parameters are what we optimize with respect to. Those are basically our free variables in optimization. Lambda is a fixed value, but it basically like defines a specific optimization problem, and that can be like this corresponds to like a penalty on having beta being too large, assuming f is some measure of the magnitude of beta, right? So something like an absolute value or a squared norm. The unconstrained approach is more popular just because unconstrained optimization is much simpler than constrained optimization, usually. So, weird. Okay. So just to rehash, model parameters, these betas, those are what we derive by the model, right? They are basically our like our slope terms and our intercept terms in our linear model. The hyperparameters are fixed parameters of the optimization itself, but we do want to tune them because we don't know, like each lambda will basically give you a unique model, more or less. And the idea is that, as I change lambda, I'm going to get, different outputs for beta because I put restrictions on beta. And the question is, which did best? Was it the fully unconstrained model where I set just lambda equal to 0, had no penalty on how large betas were? I should certainly consider that as a baseline to compare against. But as I start adding constraints, I might see that my performance actually increases as I constrain betas. That's because it is reducing the variance. And then if I constrain things too much, as you imagine, as the penalty tends towards infinity, our predictions will be 0 because all the betas will be forced to 0. So in like machine learning, like libraries and stuff, searching hyperparameter spaces is often called a grid search. So as I mentioned, we'll use the unconstrained approach. There are two popular types of regularization. There's a third popular type that I don't mention here that combines the two. It's called elastic net. But all we're doing is saying, hey, do we want to use the squared norm or the absolute value? And Last has this nice property in that it actually vanishes certain variables, whereas L2 just shrinks them. L2 is like shrinking only, whereas L1 is shrinkage combined with selection. Lasso stands for like, I forget what it stands for, something shrinkage and selection operator. We'll see what it's called again in a moment. Very important quick caveat, always standardize your predictors. As you imagine, if you have very large or very small values, it doesn't make sense to penalize them, equally. You should standardize them, so now it makes sense to penalize them equally. Okay. So for the rich case where we have the L2 norm, sum of two convex functions is convex. This is actually something that you can solve via calculus. But let me get to the grid search aspect. So if someone wanted to know, like, hey, I use this model, but I didn't use, I used some sort of ridge regression penalty on it. And they're like, why? Well, look, we increased our R squared from 0.7239 to, whatever this higher value is. But the idea is that, okay, you applied some sort of penalty that helped with the variance. It did lead to, perhaps, a noticeable improvement with respect to your R squared statistic or your mean R squared statistic. So this was kind of like when you're looking, this is again like another type of heuristic, kind of like forward selection, only really considers, one potential path across the exhaustive selection tree. This is another approach of sort of tuning down your model. The lasso really does it the best with respect to the shrinkage approach. And this was my example of cross-validation. So keep in mind that we basically averaged the value across multiple folds, and remember, like, for statistical validation purposes, right? Take your data, right, and split it up into, leave one out, basically. For example, if I did 4 folds, I would have 4 different cases where I'd, have left out the 4th fold, left out the 3rd fold, left out the 2nd fold, left out the 4th fold. And that way I have, 4 different cases I can test per model, right, per lambda value. Each lambda value that you test gives you a unique model. So keep in mind that, you're going to have to test a discrete set of lambda values. You might test like 0, 0.01, 0.02, and so forth. So it's still somewhat computationally expensive, but a lot faster than exhaustive selection. So at least, searching a grid is some sort of like quadratic type search. So one thing to note, it'll just shrink the coefficients, in the 0 direction, but it doesn't, generally cause variables to drop out entirely. Whereas if we use the L1 term, this one, we don't have a general analytic expression for it. You would just use like a gradient descent or like a simple interior point method to solve. But again, and these things aren't necessarily like super smooth, right, in practice. But generally you get some sort of like increasing up to a certain point and then decreasing for R squared. Sometimes the fully unconstrained model is the best, in which case this plot would be strictly decreasing. But lasso is really nice. It has this so least absolute shrinkage. Okay, least absolute. So it's considered a selection operator because you'll notice that, sure, things are shrinking because we're penalizing the absolute value, but at a certain point they're forced to 0 and then they stay 0. So, as lambda gets larger, it actually starts to knock out more and more of these variables. As far as interpretability, if you look at these plots, you can tell what the important coefficients and thus the important variables are, basically by looking at how far away they are from 0, right? They're all shrinking towards 0. So like this one, whatever it was, x6 maybe, right? This one at the top, x6 was our, looks like our most important variable. It looks like it would get knocked out last if we made lambda super large. But I don't think our lambda was that large. I think our lambda probably knocked out just like, the 3 that you can barely see on the bottom left, for example. So, these operators, regularization operators, they do give us, sort of, they maintain the general structure, interpretable structure of the standard linear models, and they also, help us, select which, or help us view which variables are most important. I'll come back to this if there are any questions, but basically, there's a reason why you get the, the L1 level sets are different from the L2 level sets. So that's like absolute value versus squared norm, and that's basically why it shows like why the intersections happen on the axes for one versus the other. If I think we got half an hour left, so I'll come back to that if we have questions at the end. I do want to quickly get through classification. So we're going to look, we're going to bring back that armored platform like penetration versus non-penetration classification problem. So if, this is kind of the canonical generalized linear model for classification type problems. As basically I have this logistics type curve, which is, that wavy S type thing. Right. But this is still like very interpretable because, you can still like tell the direction, we're trying to model a probability of something happening, probability of penetration versus non-penetration. And basically it's very easy to say, okay, if beta 1, has a certain value and we increase x1, well, beta 1 is -2, so it's increasing. If we increase x1, then this linear model, it looks like what we had before, is actually decreasing, right? But that's in the exponential. So the exponential is increasing in the negative direction, so it's getting smaller. The overall model is getting, the probability estimate is getting smaller as x1 increases. As far as an exact interpretation, okay, you're dealing with, probabilities now. I think when you start describing probabilities, it gets a little less interpretable. You can calculate, we'll talk about the inverse of this function in a moment. Logistic regression, we often describe like changes changes in the variable with respect to log odds of the classification. But odds in themselves are not inherently like super obvious, I guess, to me at least. So for actual classification purposes, like since you're assigning probabilities, you need to have some sort of like decision rule. I mean, sure, you can provide a probability and like, all right, I predict 60% probability it penetrates. You need to assign that an actual classification. And the usual rule of thumb, the most efficient one is, if it's greater than or equal to 50%, then assign y equals 1. If it's less than, assign y equals 0, or 1 and 0, or penetration, non-penetration, respectively. So the only issue with that is, depending on what you're doing, you may want to be more strict with respect to things like false positives or false negatives. So you can actually like set, you don't have to use the 50% threshold. You can adjust that threshold as you see fit. I'll talk about that a little bit later. One thing we have to watch out for is, unlike the squared or absolute value loss, coming up with a good classification loss can be a little tricky at times. Like the most obvious one ends up not being convex. So we do something, this is pretty similar to, I think, what's called the cross entropy loss. And the idea is that this does give us, this is a convex alternative. And, if you were to like kind of look and stare at it for a little while, it would make sense because, don't forget the negative sign. But like if your probability is close to 0, right? This will be pretty negative, right? And but if the yi assignment is actually 1, right? That means it's an error, right? But if your yi is 0, then that's going to vanish anyway, right? So it doesn't matter. And then you can look at the other side in the exact same way. Yes. So one thing I mentioned, so there's that log odds interpretability. So keep in mind that, the logistic function is just basically saying, this is the standard logistic curve function with mu as an argument. But mu, we're substituting this linear equation instead, right? And, if we take the inverse, that's saying that, the log odds change linearly with respect to, our variables. Again, log odds, like what are odds? Like, 1-to-1 odds is 50-50, right? 3-to-1 odds, you would need, what is it? 1/4 over 3/4, right? And things like that, or 3/4 over 1/4. So it's like, odds are a little weird. It's easy to get things backwards in your head. But that said, at least like the directionality and like magnitude of probability movements at a definitely directionality, magnitude at a log scale. As I mentioned, there are true positive, true negative rates, false positive rates. Sorry, excuse me for the small typo where I wrote true positive and true negative for clearly the false parts. But, a lot of the time you're going to be looking at overall classification accuracy, right? Correct classification is over the total number of observations, but also keep in mind that, if we're only concerned about classification accuracy, I think that 0.5 threshold is great for the for our assignment rule. But keep in mind, making in high stakes decision making, right? False positives and false negatives, could carry like extreme penalties associated with them. A lot of the times, these things are presented in some sort of confusion matrix. Obviously, this can go beyond just binary classification, right? You could have multiple labels. Thus, if we had 3 different labels, right, we'd have 0, 1, 2, right? And we'd have a 3x3 confusion matrix and so forth. But usually what I like to look at, and this is, people like to tune that sort of decision threshold for their classification problem. 50-50 would be maybe, I don't know, we're probably somewhere close to the center of the blue curve, which is something that we would get from a logistic model. But the idea is that I can, if I have a big problem with false positive rates, am I willing to accept a lower true positive rate in order to get, a smaller false positive rate? Of course, the extreme choice is to be like, everything is negative, in which case I never get a true positive, I never get a false positive, right? And that's kind of the extreme case of D. You could go the other way as well, right? But, in some of the cases, maybe, I don't know, who knows, maybe D, 0.5 was over here. I don't think it was. But the idea, maybe if, wait, you can't see it. Maybe it was like up here or something, right? And it doesn't look like you're losing much with respect to true positive rate by moving to the left, but you're already chopping off like a good, maybe like 20% off of your false positive rate. Okay, so I introduced these concepts. So, pretty much for all machine learning models I can think of, you're going to have some sort of optimization problem. And then you always have to watch out for, bias variance trade-off, which, popular approach is, again, regularization or some sort of variable selection approach. Let's see. So we've talked about like kind of statistical validation in order for testing our models, and then the multiple model selection problem. I'm going to talk a little bit about my favorite class of machine learning models, which are decision trees. And that's because they can, as with most things, they can get arbitrarily complicated, right? But the idea of a decision tree is, I think it's like I think it's more interpretable than linear regression, in my opinion. So it's, you can use them for regression, you can use them for classification. I mean, they're called decision trees. You can use them for optimal decision making. But the idea is, we're going back to kind of maybe our canonical regression example. But basically, you have things like combined flight hours, previous month's demands, and you can basically, create a tree that gives you a demand prediction value. Building out the tree itself is the hard problem, right? I mean, you could, these splits might look arbitrary, but they're not going to be arbitrary. They're going to be chosen by an optimization problem. But I will say that a lot of people doing research in machine learning struggle with formulating a good optimization problem. In fact, some of the latest work on decision trees is just coming up with a better optimization problem for building a decision tree. And some of their papers are as recent as this year. But the idea, hopefully the concept is simple, right? Of just follow the tree and you reach your prediction value. It is creating kind of a nice partition of your feature space. So this would be like all possible predictors, and then you're partitioning it into different regions. And the idea is for regression, usually what you'll use is all the points that fall within that area, like the light blue region on the left, for example. The average value would be your regression prediction, right? Whereas if it was a classification problem, then you would just use the most frequent class. And usually when you're doing things like the optimization problems, we'll try to do things like try not to have too much class mixture within each region, because it would be weird if you had 49 of one and 51 of the other, and it's like, well, that's not great for classification purposes because it seems like 50-50. And then for regression, hopefully you don't have too much variance within a single region. This is, nonlinear behavior is easy to model decision trees. I would say if you want to use nonlinear modeling, I would say there are simpler ways to do this, because this is based off branching and bounding, which sure, I can build a staircase to approximate any weird geometry, right? But it is somewhat elegant in how simple it performs, and quite frankly, it does really well compared to a lot of machine, in practice. I think you'll hear that some of the best off-the-shelf, even today, some of the best off-the-shelf machine learning models are like XGBoost or CatBoost, which are still beating out the neural networks for the super fancy transformers with respect to certain types of data, especially economic and operational data, where it's not involving images or free text. So I introduced you to the idea of single decision trees, but there are also you can take an ensemble of them. This doesn't just have to be decision trees. You can take an ensemble of any type of model, right? Some ensembles you might not want to do. You might not want to do an ensemble of linear regression models, because the argument might be, why don't you just collapse them into one? But for decision trees, there are various approaches. Random forest, I think, is maybe one of the simplest to understand. If you're to do some further reading on your own, it just decision trees, you can grow them very deep, and as they grow deeper, as you imagine, you run into that overfitting issue where you have high variance, low bias but high variance. One thing to reduce variance is by averaging across several values. I think we remember that maybe from elementary stats, where we looked at the distribution of an average, right? So it just applies that approach to multiple decision trees, and then that way you've kind of counteracted the too much variance. Random forest also incorporates a special approach for dealing with highly correlated trees. I won't get into that. And then the boosting methods are feel almost like an extension of random forests, in that an average is a weighted sum where all the weights are the same, right? Boosting, again, there are many different ways to boost, but the very general principle is you're taking a bunch of trees and then kind of weighting, doing some sort of weighted average. I will say, when you start bumping up the number of, random forests, like 500 to 1,000 decision trees is pretty standard from what I see. And once you're up there, it's a single decision tree is highly interpretable, but a bunch of decision trees, well, it's a little hard to see It's a little harder to interpret. You can still do these things with variable importance plots. For example, in our canonical regression example, maybe I did some sort of XGBoost, and I looked at the variable importance plot. And the idea is that, sure, I've got maybe 1,000 decision trees, but in the vast majority of the decision trees, perhaps all of them, planned flight hours was the first split. And if it's the first split, that means it was like the most important decision to make, right? Like the splits towards the end are least important, or not least important. The least important are the splits that don't occur. But the idea is, splits closer to the top of the decision tree are the highly important ones, and the splits further down are less and less important. So I did mention this one particular lab. I see a lot of research on decision trees that is still focused on kind of like ensemble type approaches. But I'm always still looking for more optimization type approaches on growing decision trees. Cynthia Rudin is one of my favorite decision tree researchers. So she's located at Duke University. I think she regularly goes to Informs, if any of you go to the Informs conference. I know she recently won, some of you know things like Fields medals and stuff like that. She basically won like the Fields Medal of AI and got like $1 million. But yeah, fantastic website you can check out. I listed some of the more salient papers towards the bottom here. I think this will be made available to you all. So going forward, I did want to talk about, what do I do? I mean, if I'm dealing with images or free text, like I tend to go like the neural network route, just because networks are so easy to program now, and also like there's this book called Geometric Deep Learning, and they do like a really nice, almost. I mean, it's a math book, but it makes some interesting like linguistic arguments about free text and the nature of images. But images and text just have kind of a nice format that is conducive to like certain things like convolutions and attention mechanisms. These are things that you see in neural networks a lot. And a lot of that stuff doesn't really make sense for tabular data. For tabular data, some people say like causal inference, which me and some of my colleagues say should be called conditional inference, not causal. My usual shot for tabular data, like the type of examples we saw with the demand prediction, I would go like XGBoost or CatBoost. I like CatBoost just because it has a ton of cats in the documentation. If you're working with subject matter experts, obviously you want something as interpretable as possible. That way they can, point at something and be like, nope, that's wrong. And then you can have the discussion, why is that wrong? Then you find out something's wrong with the data, not your model. Your model did everything to the wrong data. So I think, working with interpretable models like decision trees, linear regression really helps with, dealing with data issues and diagnosing all sorts of different problems. Just keep in mind, sometimes your data, especially if you're working in DoD, sometimes your data is like some person wrote it on a sheet of paper and then someone like manually keyed it into the database or something. So expect there to be some errors, and interpretable approaches can really help with that. If I'm dealing with a large feature space, but I want to maintain my interpretability, that's usually where I go the regularization approach. You don't have to apply regularization to just linear models, right? You can apply, regularization to pretty much anything, right? That has a mathematical formalization. Ultimately, my general goal is, try multiple models and compare. I mean, if I'm trying to do something that's like, a really challenging forecasting problem, I feel like I should, at least see how well, some sort of, recurrent neural network structure can perform compared to, ARIMA or ARMA model, simple time series model. Because, yeah, you might get a better fit. You don't quite understand the black box because it's got too much structure within it. But maybe it's maybe the improvement is, is the juice worth the squeeze, I guess is the saying I was looking for. So yeah, try multiple models. Even for text and images, I can think of examples where like I was able to apply something that, and now again, this is when like AlexNet was state of the art. But I was still able to outperform a lot of like CNN's convolutional neural networks with more interpretable approaches that use things like non-negative matrix factorization, which is an unsupervised learning approach. Hey, I was trying whatever I was engineering whatever I could to try to squeeze out the better performance. But the idea is bottom line, try different models. So getting familiar with optimization, the language of optimization is generally the same within numerical and like numerical optimization, like the field. And then they'll like change it slightly for machine learning, which is highly frustrating to me. So it's like loss functions versus objective functions. But the idea is generally like you're minimizing some sort of function subject to constraints. This isn't telling you anything about whether you have to, use an interior point method or, stochastic gradient descent or whatever to solve it. All you know is that you have, here's a function, and I assume this function is a measure of badness, and here are these constraints. And a lot of optimization, you can get some nice crash courses online if you just look at like linear programming or quadratic programming, because like the lasso model, which I introduced earlier, is usually you can solve it via gradient descent. I think a lot of people just solve it using linear programming, which is an easy way to encode those absolute value operators. So again, being aware of hyperparameters, that's that whole like grid search feature, and it's hyperparameters again. They like specify different models. So dealing with multiple models, I said test multiple models. So you're going to test multiple models across multiple hyperparameters, but you should also test different like categories of models, like decision trees versus linear regression, support vector machines versus neural networks, for example. Those have like completely different architectures from a mathematical perspective, and it's interesting, to see like how some can outperform others in various data cases. So I provide some recommended further reading. I basically pulled, like this was almost like a pull out of the, I call it the, I guess, ISIL, Introduction to Statistical Learning was basically this was like a quick coverage of some of the chapters of that. That one's nice. They actually have, it's available free online if you just go to statlearning.com. And the nice thing about it is, since this is a mini tutorial, I had to decide, do I want to include coding? I was like, hour and a half, like live coding exercises, probably not. This one, it has all, and luckily, since it's web access, you can literally copy and paste code right into your development environment. Got R and Python versions. The elements of statistical learning, I don't think it has. I know it has some like outputs from code. I don't remember seeing any code in that book. It talks more about the theory, and it does talk about like some more complex stuff compared to Introduction to Statistical Learning. So XGBoost and CatBoost, both of these actually have very good online documentations that not only talk about the theory behind them, because have to learn about the gradient side of gradient boosting, and like CatBoost is specifically dealing with categorical data, which can sometimes pose problems, even on a computational side. As I mentioned, Dr. Rudin's Interpretable Machine Learning Lab is great. If you just look up Cynthia Rudin Interpretable Machine Learning Lab, you will find a very easy to navigate website with tons of resources, including papers, run code that you're able to run. And I don't think I have a whole lot more to say other than, are there any questions? I don't feel sick anymore. The adrenaline will wear off, but
Including from the internet.
So you talked about decision trees. How do you decide how deep you go with the decision?
yeah, so for decision trees, you can actually, like one approach is to basically, it's like tuning hyperparameters. You can have a term in your objective function. I actually might have it on one of these backup slides. Yeah, so like you could find like the best. So usually when you're tuning a decision tree, you're trying to find the best splits up to a certain point. But you can also penalize by the number of splits you have, and then in this case, like alpha is like your lambda. Like you could try a bunch of different alpha values for penalizing the depth of your decision tree. This was all done in the context of binary splitting, which is like the simplest algorithm and still popular. I mean, it usually does pretty well in practice. That's a greedy algorithm for splitting. But yeah. As far as deepness of growth, that's one approach for it. For things like random forests, they're kind of like, I think a popular upper limit is like the square root of the number of predictors should be like the maximum depth of each decision tree, and then you can grow less than that. Yeah.
I have a question.
Yeah.
So we're interested in analyzing psychophysiological data. And I think that machine learning might be very practical for specifically EEG data. For example, we have a data set collected like in a flight simulator of a 10 electrode EEG system, but it's highly correlated and it's a lot of data. So I guess my question is, do you have any advice for extracting informative information from that, or reducing the dimensionality or severity?
Yeah, so as far as extracting structure, I know for like those types of things, a lot of like graph-based algorithms are popular. I don't really, this is more like what I know my colleagues have done. Because when I was at Chapel Hill, I didn't work so much with the medical school, but a lot of my friends did. I know like one of my friends focused very much on like graph structures of the brain. You said, are you trying to extract correlations, or that could be a part of it?
Not sure really what the end goal is. We're trying to characterize mental workload.
Yeah.
That is.
Yeah, so graph structure would be nice because like you'd have readings from each, I guess, part of the brain or something like that, and then you could, that would be a node in the network, and then you could basically like, form some sort of optimization problem to build the correlations between them. I could maybe I'll have to give you my email because I might be able to point you out towards, I can't remember a methodology off the top of my head, but I've definitely like read some of the papers on it a while ago.